Okay, so probability distributions. This is really just talking about a listing or a graph that represents all the probabilities that could occur for any outcome in a distribution. All right, so you're looking at, like, for example, the roll of a die. The possible outcomes are 1 through 6, and so a probability distribution would be just us assigning the appropriate probabilities to each one of those outcomes. All right, so 1, 2, 3, 4, 5, and 6 are the represent the complete list of possible outcomes for the roll of a die, and the probabilities that go along with those are all the same because you have an equally likely chance of getting a 1, 2, 3, 4, 5, or 6. So we would just represent each one of these, or just use 1 over 6 to represent each of these probabilities. Now you can see how this could get a little spicier if you had a more complicated situation, because if the probabilities aren't all the same, then well, that in and of itself makes it more challenging. But then on top of that, you have the part where it's like, well, what if I'm not given the probabilities, even if they are different? What if it's hard to come up with the probabilities of each outcome individually? That could be part of the challenge, right? But before we get to that, we'll talk about the concept of the mean and standard deviation in this context, which is, it's good news. Maybe not so great news is that the notation changes a little bit. So the mean is represented with a lowercase Greek letter mu, and the standard deviation is represented with the lowercase Greek letter sigma. All right, and that's because we're dealing with population means and standard deviations rather than sample means and standard deviations. All right, so population measures are always represented, or at least in this context, using the Greek letters. All right, so this is the not so good news. The calculator doesn't always use the Greek notation, so sometimes we have to parse out based on what the calculator says, and try to figure out what part is relevant to us and what part isn't, right? But the good news, in fact, the great news, is that finding the mean and standard deviation is exactly the same keystrokes as it was in the previous unit, right? So we go into the calculator, the stat editor, and we just type in all this data into L1 and L2. All right, so 1, 2, 3, 4, 5, 6. And I guess maybe it's slightly annoying that you have to type in 1/6 6 times, but could be worse. So, and it converts it to decimal form, which is fine. It's just you wouldn't want to have to put the decimal approximation in there yourself because you could lose accuracy that way. When the calculator does it, it puts the most accurate form of the decimal of the fraction that it could come up with in decimal form. But if you do it, odds are you're going to be rounding in some capacity, and you'll lose some accuracy. So you got to be careful about that. All right, so just put it in as a fraction. Let the calculator convert it over for you. All right.
So if I put it in as a fraction again?
Oh, just 1 divided by 2. Yeah, just type it in as division.
Oh, you said 1 divided by 2? I did.
Oh, I'm sorry, 1 divided by 6. I misspoke. Oh, Saturday morning. Still waking
At least you
up.
don't have the cough today.
Yeah, coffee worked. Nah, I think it's the copious amounts of antibiotics that I was taking.
Probably.
Yeah, I forget which one it was, but it's like the heavy duty one that they tell you that once you finish it, you have to start with the probiotics afterwards because it kills like all the bacteria in your body, including the good ones. No, no, it's like Cipro something or other. Yeah, well, yeah, something along those lines. But it's
500 milligrams, right? Or 250?
honestly, yeah, you could tell I'm not medical. It's like, what's your I don't know, whatever the doctor
Do you
put
have
a
to use it for 10 days or just 7 days?
10 days. Yeah. Because I had the sinusitis at the same time. So now they got me on the Flonase.
That's for the month.
Yeah, for like the rest of my life.
For the rest of your life?
Yeah, it's wonderful. They said something about checking with my doctor again after 6 months. And I'm like, wait, what? How long am we supposed to be on this thing for? And they're like, oh, you're
Every morning and twice at night.
yeah. They're like, you're on this for good, man. Like you get a sinus infection every like 6 months. You're like,
Have you seen an allergy doctor? Because they told me the same thing, and then they told me to go to an allergy doctor. So you got to check out for that too.
I went to the allergy doctor. I had sinus surgery, and that just opened the floodgates. Because before I had a deviated septum and I wasn't like breathing through my nose, so I would never get a sinus infection because nothing was going through there. Then they opened it all up, and then boom.
Man.
So you had the surgery for the deviated septum.
Yep.
Did that help, by the way?
I can breathe through my nose.
Okay.
The problem is now I'm inhaling everything through my nose, and including pollen and everything that apparently I am allergic to. So, yeah. I was fine being a mouth breather too. It's just the problem was the snoring was, I guess, the problem. But whatever. What can you do?
Does your CPAP machine help you?
CPAP helps. CPAP, I get a good night's sleep. And, I don't wake up in the middle of the night gasping anymore, so that's a win. We'll just take that where we can get it. So anyway, quit out of here. Stat, calc, option 1. All right, so just like in the previous unit. Hit enter. It asks us for a list 1. Frequency list is my list 2. If you have one of the older calculators, you might have to type in L1 comma L2. Hit calculate, and it gives us this display, which is very familiar because, again, if we needed the median, the standard deviation, the 5-number summary, all that stuff, we were getting it from here. There's a slight bit of interpretation that we need to do. Very slight. The 2 relevant pieces of information are the X bar and the sigma X. The sigma X, I think, based off the notation that I just introduced, that should be obvious. The one that's not obvious would be the X bar. That is mu. Even though it doesn't say mu, in this context it's mu. The calculator actually has a hard time, these calculators have a hard time making curved symbols. So that's why you don't really see a lot of lowercase letters. And when you do, they don't look so good. So like when you see 1 var stats, that A looks kind of funky, right? So they purposely avoid trying to make curved letters. So a lot of what they use are capitals. And so they just didn't make a function to give the mu because they figured, they'll just know that the X bar means mu sometimes. And unfortunately, that's not always the case. Right? Not everybody knows that. Right? So we know, because we're dealing with a population, that any mean that we get should be a mu. But the big question would be, how do we know that it's a population? That's a great question. And that's where this little nugget here comes into play, where it says sigma, that capital sigma, which means sum of P of X, what should that be equal to? It should be equal to 1. 1 represents 100%, which means all outcomes. Oh man, calculators has a hard time with curved letters. Yeah, not only the calculator. All outcomes. All right. Anytime you have all of something, you're dealing with a population. All right. If you have part of something, you're dealing with a sample. All right. It might not be a good sample, might not be a representative sample, but it's definitely a sample. All right. So you as a group are a population and a sample, because you're a sample of students at WCC, but you're also, if I define my population the right way, you're a population of statistics students for me, because I only have the one stat class, so you represent all of my stat students for this semester, all right? Or maybe you could be a sample of all the stat students that I've ever had, right? So depending on how you define things, you could fall into either category, right? So identifying when it's a sample, when it's a population is really important. But the good news is, in probability, it always has to be a population, because a probability distribution must add up to 1. It must account for all possible outcomes. So if that's the case, then we're always going to be dealing with 100%, and therefore always dealing with a population, and so therefore always dealing with mu and sigma for probability distributions. And the added byproduct is the calculator is going to tell us this. So these two lovely looking formulas, you're not going to have to worry about them, because they're built into the calculator. And just like we talked about in the first unit, I'm sure there is some value at some point to knowing how to use these formulas, but that's kind of after the fact. What we want to know is what the mean and standard deviation are and how to actually use those numbers, not necessarily the formulas. Right? So we do have to get into the interpretation of what the mean and standard deviation represent, but that's a different conversation, which we'll get to in a few minutes. Right? So, but in order to understand it, we have to talk about what are known as discrete and continuous random variables. The discrete random variable is a countable random variable, and the continuous is the non-countable, or something you need a measuring device for. So an example of discrete would be sides on a die. All right, so basically what we just did. Sides on a coin if you want. All right, cards in the deck. Marbles in the bag. All right, anything that you could physically count. All right. Continuous random variables would be something like heights, weights, temperatures, anything that you would need some sort of measuring device to determine the value of. All right. If I can look at it and determine its value, then it's probably going to be discrete. If I need a measuring device, then it's going to be continuous. All right, so chairs in a classroom, light bulbs, things like that, discrete. The length of time that it takes for me to get from here to home, that would be continuous. All right, and so it could vary from person to person. So loosely, you might consider discrete random variable situations as being like your math class type problems, and continuous random variables as being those real world applications. Right? It's probably a good way to think about it, because I've been saying this all along. We're learning about the cards, the dice, the marbles, and all that stuff, so that we can expand it to the real world. Right? So it's really making the transition from discrete to continuous that's really what this is all about. Right? So, you know, like how medicine is absorbed into the bloodstream, you know, at what rate, things like that, that would be continuous, because you can't just count it. You know, you have to have some sort of measuring device. A probability distribution graph is very easy as long as you have the table available. So for one roll of a fair die, since all the outcomes were the same, we're looking at 1, 2, 3, 4, 5, and 6 all of having the same height. So what I could do is just kind of extend my graph and break it up into 6 equivalent regions. Roughly, you know, it's not perfect. Or it doesn't need to be perfect. Also, you can kind of blast through this because we're beyond the phase of the course where I'm interested in asking you to create graphs. So I've already assessed you on that, so this is really just getting a sense of what some probability distributions might look like. All right, not really assessing your ability to create a graph. You could put the height of 1/6 anywhere you want because it's not going to change. You go all the way to the top if you want. We're going to have 6 bars that are exactly the same height, assuming, of course, I could draw it correctly. And so that's what the probability distribution graph would look like for one roll of a fair die. It would look very similar if you were flipping coins, except you'd have 2 bars instead of 6 bars, but they should have the same height, 50-50, 0.5 or 1/2. All right. If the probability doesn't change, we call that a uniform distribution. All right. So it's uniform throughout. Probabilities do not fluctuate. Now, again, we do want to try to tie this to the real world. So you go out, you collect a data set like I did with my barometric pressures, and the heights were roughly the same, right? Well, the real world doesn't always follow a perfect trend, right? So to come up with a height of 1/6, no matter how many trials you conduct, that's not always going to play out. So the real world adaptation of this would be something roughly the same height, right? So we would still call it approximately a uniform distribution if the probabilities were very, very close to one another throughout. Because unless it's something like rolling dice or flipping coins or pulling marbles from a bag, you wouldn't necessarily expect real world phenomena to play out perfectly like it would in a math class. All right. So we jump to something that may not be a uniform distribution. And by may, I mean it's definitely not. I mean, you don't need to read the problem to know, because you just look at the P of X column and you see that they're definitely not all the same. All right. So the question says to graph the distribution. We'll just kind of hand wave around that, because really the goal was to make a determination of what kind of distribution it would be. If I were to rough out this graph, you would see that for the low and high values of X, you'd have small probabilities to be very close to the X-axis. And as you work your way towards the middle, it gets taller and taller and taller until you get the big hump in the middle. That would end up being something that looks approximately normal. So you can create the graph if you want, but the only purpose was to see that it would not be a uniform distribution, that it would look approximately normal. All right. And the justification for that, the justification for me asking the question, or the purpose for asking the question, is to allow us to use this rule. This is part of the empirical rule. The empirical rule applies for populations as well as samples. So mu plus or minus 2 sigma will help us determine whether or not there are usual or unusual values in a data set. Well, definitely there will be usual. It's a question of whether there will be unusual. And you could see that it's reliant on mu and sigma. So I need to know those two values, and if I know those two values, then I'll be able to perform this calculation, and if I do that, then I'll be able to determine what is unusual. Now, contextually, because you never want to blast past that part of it, we're talking about 14 births. I would imagine it's not by the same person, although you never know. But we'll assume that 14 births are selected at random. And we want to know whether it's unusual to get 13 girls among those 14 births. My sense is probably. You know, like it's not impossible, as we know, but it's one of those things where it's like, is it a shocking outcome? All right, so you walk into what do they call it? Is it neonatal? That my son was a preemie, so it was the neonatal ICU, so that was different. But you know, like the nursery at the hospital, you walk into the nursery and you see all the little babies in the beds, and they're adorable, and some have the pink blankets, some have the blue blankets. And, you know, I don't even know if they do that anymore, honestly. But yeah, you look around and you're like, oh, there's how many we have here? 15. Whoa, 14 of them are girls. It's crazy. Didn't see that coming. Not impossible, but it's like, wow, I didn't see that coming. You know, but if it turns out that they're all girls, or half of them are girls, or one of them is a girl, or whatever, nothing is like shocking. All right. Now, if it turns out that they're all like little chihuahuas, you know, you go in there and you're like, wait, I expected humans to be here, and they're not. Then, oh, whoa, that's shocking, right? That's you're getting into outlier territory there, or like 40-year-old men laying in those beds, right? Now it's like, whoa, we just got into the realm of Twilight Zone. So, but nothing is shocking. It's just a question of whether it would be unusual, or, you know, like you have 14 births, but there are 20 girls. All right, now we're in shocking territory, because now we're talking like twins or triplets and things like that. Like, this is beyond like, didn't see that coming. It's like, not only are they all girls, but there are like triplets involved. Like, okay, something weird's happening here. All right, so any distribution gives you license to investigate whether there are unusual values, but the context gives you even more so of a license, because you're looking at it like, I'm interested in seeing what the outcomes are here. Now, I'll give you a little background on this. I got this problem from a textbook a long time ago, but it was sourced from real data. It had to do with, I think it was a Chinese calendar, like the gender selection. And so, but it was a gender selection technique. I'm pretty sure it was Chinese calendar, but it was basically somebody saying, follow what I tell you to do, and I can guarantee that you're gonna get a girl. Like, you want to have a baby girl, this is how you do it. Like, you got to conceive in this period of time. You know, like, you got to be this age and so on. You're basically following the Chinese calendar, and so this is what the ordinary distribution of outcomes would be. Like, not having to do with the Chinese calendar, but having to do with just nature taking its course. This is a binomial situation, which we'll talk about in a few minutes. 2 outcomes, male, female, 14 trials. This is what the probability should be if there were no interaction, right? So what we would be determining is the likelihood of getting 13 girls among 14 births, or whether that's unusual. And so if it is unusual when nature takes its course, but it happened anyway, then that's telling me that there must be some outside influence somewhere. All right. So that's the thing behind inferential statistics. If something is so ordinary, so out of the ordinary that it shouldn't happen, but it happens anyway, and there is some imposed influence, then there's reason enough to conclude that that outside influence may be what caused that effect. All right. So this is the beginnings of that. So 1, 2, 0, 1, 2, 3, all the way up to 14. So I gave all that context, but it basically boils down to type it in your calculator, find the mean and standard deviation. So you can still get questions right without understanding the context. It's just, it adds a little bit more flavor to it, you know? It's the sun-dried tomatoes in your salad. They don't need to be there, but it gives it a little extra. Double typed. All right, so screwed something up, so let me go back and find it. Oh, I missed a 9. All right. And 0.21 is wrong also. Oh, it's equivalent. It should be fine. Yeah, because when you type in the 0.210, it just, the calculator drops the 0. Same thing with the 0.000, it just makes it a 0. Let me just double check everything else while I'm here. 3 is 0.022, not 022, not 002, I mean.
If you put 0.210, can you give you 0.21?
Yeah. Alright, so that gets typed in. Same process as the last question. Stat, Calc 1, L1, L2. A little calculation here. And we get our summary statistics now. Well, parameters. Some parts of it should make sense, and some parts of it are like, I'm sure in some world it makes sense, but I don't know what it means, and that's, I guess, what I'm here for. The x bar, we interpret that as mu, and the 1.875 blah blah blah, all that stuff, that's our sigma. Now, another name for the mean of a probability distribution is also known as expected value. In some situations, it has more meaning than others. Like when you roll a die, a single die, all outcomes are equally likely. So we got a mean of 3.5 for one roll of a die. If we interpret that as the expected value, I don't think anybody's expecting to get a 3.5 when they roll a die. But if you have a distribution of births, 14 births, and I want to know how many you expect to be girls, like most people are going to say something in the neighborhood of a 50-50 split. So 7. All right. So in this context, it makes more sense Yeah, if you've got an 8, then you probably typed in something incorrectly in your X column,
Thinking.
your L1.
But the sigma number is the same.
Right, that means probably your P of X is probably all right. So just double check your L1 and make sure it's 0 through 14. So then we just have to run the numbers. Mu plus or minus 2 sigma. So 7, that's interpreted as 7 minus 1.875. 0.99. Just get as much of that decimal in there as you can. That's going to be our lower bound. And then same thing but with a plus sign. So 7 plus 1.875 blah blah blah. Because the calculator is going to do it for us anyway.
Do you have to multiply?
Times 2, thank you. I'm struggling so much to write here that I can't even think. It's like I have to put all my body weight into this pen, and it's literally killing me. Literally in the figurative sense.
Is your lower back?
Nah, it's elbow right now. So, yeah, I developed a little bit of tendonitis at some point.
What is that?
7 came from the mean.
When you have a chance, can I get some help here, please?
Yeah.
May I come?
Yeah. You may approach.
I went back to the list, and I know I missed to insert the 0.
So go to. You typed that incorrectly, so let's go stat, edit.
Okay.
So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
To insert was second insert. That's how I
10. Right.
remember.
So that's good. It looks like you just need a 0 at the end here.
Maybe when I switched it at the
When
end.
you added it in, you're
Sorry.
1 short at the end. So now this should run
Okay.
correctly. There you go.
Uh-huh. And now back to that stuff? Just
Yeah, now you're just typing this in.
Okay.
So we type in the whole decimal the one time, but then the second time, it's just a little copy paste action. So the usual interval is going to be happening between, and we could do a little bit of rounding, approximately 3.25 and 10.75. All right, so they were just asking us about the number 13, but there are actually a lot of values that are unusual. So I'm going to just identify the usual interval here. Anything more than 3.25, anything less than 10.75. So these are the usuals. Which, when you think about it, should make a lot of sense, because if you're talking about 14 births, to have this kind of variation in gender, that kind of makes sense. You know, like if I have 7 girls, 7 boys, that's the even split. 8 girls, 6 boys. 9 girls, 5, 10 and 4. Okay, now it's starting to get right to the edge of what I would consider to be usual. Then after that, now 11 and 3. Okay, it's getting a little out of the ordinary. 12 and 2, 13 and 1, 14 and 0. Right? And the other way around, if I had no girls, or only one girl and 13 boys, 2 girls and 12 boys, and so on. but this is the sweet spot of what I would consider to be the usual values. Since they were only asking about 13, that's the only conclusion I need to draw. So therefore, 13 girls would be unusual. All right, 13 girls would be unusual. Now, you might look at this and say, well, I kind of knew that, because the probability of getting 13 girls in 14 births was 0.001. So that's 0.1%. Like, I mean, without knowing what the cutoff is for something to be considered unusual, you might say, well, 0.001, that's going to be unusual. It's a very, very small probability. Even 0.022, 2.2%, that's something that's considered unusual, right? So anything, as it turns out, anything that occurs less than 2.5% of the time is going to be considered unusual if it's a normal distribution, because 2.5 will be on the low side, 2.5 will be on the high side. But generally, we want to know the values that would be the cutoff, and so this ends up being the easiest way to do it. All right. And also, there's some little shortcuts along the way that'll help us figure this out. Page 35.